Hello and welcome back to this channel. Dear students, this is the quick revision session. So first topic is MOSFET parasitics and technology scaling. Whenever there is a manufacturing of MOSFETs, then due to the structure of MOSFET, different internal capacitors are created. These are called parasitic capacitors. So this is the model which shows the effect of or existence of parasitic capacitance. We know that in case of MOSFET, there are three major terminals: source terminal, gate terminal, drain terminal. This part is the part of substrate, which is also called bulk. As I said, these capacitors are created due to the structure of the MOSFET. We know that in simplified language, if two parallel plates are there in case of parallel plate capacitor, and between them certain dielectric is existing, then it gives effect of capacitance. Likewise, if I'm talking about this capacitor C1, look in the diagram, it is connected between gate and this part is source terminal. So C1 is overlap capacitance between gate and source. C2, this capacitor is overlap capacitor between gate and drain terminal. Then C3, gate to channel capacitance. Between below this part, the channel is created in case of a MOSFET. So C3 is the gate to channel capacitance. C4 is source to substrate junction capacitance. This capacitance. This part is the part of source. So C4 is source to substrate. This portion is related to substrate. So source to substrate junction capacitance. Same way, C5 is drain to substrate junction capacitance. Now C6, this capacitor is the depletion capacitance between channel and the substrate. So these are the different capacitors which are called MOSFET parasitic capacitance. Next part is technology scaling. From the exam point of view, you may expect the short note or explanation of this technology scaling methods. As the name indicates, scaling means we are supposed to reduce down the dimensions of the device so that we can accommodate maximum number of devices in an integrated circuit. So there are two types of scaling technologies. First is constant field scaling. Second is constant voltage scaling. In first type, constant field scaling, the dimensions of the transistor, then device voltage and doping concentrations are changed, rather reduced by scaling factor S. This notation S represents the scaling factor, that means amount by which we are making changes in the dimensions of the device, and this value is greater than 1. Then in case of constant voltage technique, as the name indicates, the supply voltage is kept constant while the process is scaled down. So this is the list of parameters which shows what is the effect after scaling. For example, in case of channel length, the value becomes L by S. That means original channel length L is reduced by factor S. Width is also reduced by factor S. Then gate oxide thickness, it becomes 2x upon S. Gate oxide capacitance, it is S times COX. S is the scaling factor. ड्रेन करंट, अब देखो ये जो तीन पार्ट है, फर्स्ट थ्री पार्ट्स, दीज आर कॉमन फॉर बोथ द मेथड्स. इन केस ऑफ ड्रेन करंट, for constant field it is id upon s, whereas in case of constant voltage it is s into id. Threshold voltage in case of constant field vt by s, whereas this remains vt, there is no change. ऐसे याद रखना है. constant voltage technology में all voltages remains constant. Then power supply voltage vdd by s, this remains as it is vdd. Then gate source voltage vgs upon s, this remains again unchanged, that means vgs. Channel resistance, in case of constant field, it is unchanged, it remains RON. Whereas in case of constant voltage, it is RON, that is channel resistance upon S. That means it is reduced by factor S. Power dissipation, in constant field, it is P upon S square. Whereas in case of constant voltage, it is S into P. Now let us discuss advantages and limitations of technology scaling. So advantages includes the capacitance is reduced. Downward arrow indicates reduction in the value due to decreased dimensions. Then improved current capability and it increases the device characteristics. RC delay decreases. This upward arrow indicates increase, values are increasing. Downward arrow indicates the particular things are decreasing. Then integration density is improved. It enhances the speed of device and cost of the chip, total chip gets reduced. Disadvantages or limitations: power consumption per unit area is increased. Gain of the device is reduced due to reduction in the mobility of carriers. Current handling capacity decreases. See, it improves the current driving capability, but the current handling capacity is reduced. Packaging density is increased, so it will cause improvement or increase in the device temperature. Then oxide layer may lose its dielectric property, so many times it is required to change the oxide layer, and there is an improvement in the noise signal. Next part is CMOS inverter. As the name indicates, it is the circuit which produces inverted output. Means at the input, if you are applying logic low, you are getting logic high, and vice versa. So the circuit is pretty simple. It consists of two MOSFETs, M1 that is P MOSFET and M2 that is N MOSFET. This is VDD which is connected to P MOSFET. N MOSFET is connected to ground. At the output, we are connecting capacitor C. Now, if the input voltage is low, this applied input voltage is low, then M1 is switched on and M2 is switched off. Since M1 is on, VDD will be directly available at the output. It will charge the capacitor C. Then output will be high. So we are applying low input and you are getting high output. Second case, for high input voltage, the things are interchanged. That means in that case, M1 is off and M2 is on. M2, that is N MOSFET, is switched on. It is connected to ground, so capacitor gets a path and it will start discharging like this. So output becomes zero. That means by applying high input, you are getting zero output. This is the transfer characteristics of CMOS inverter. It is graph of V out versus V in. I have marked different regions in this diagram. So region A is characterized by input voltage is between 0 and VTH. VTH is the threshold voltage. In this case, M2, that is PMOS, is cut off and M1 is in linear mode, so output is VDD. Region B, this region, in this case M1 is linear and M2 is saturation. Keep in mind, M1 is P MOSFET, M2 is N MOSFET. In region C, both M1 and M2, this is region C, both M1 and M2 are in saturation. Region D, M1 is in saturation and M2 is in linear mode. And region E, M1 is off and M2 is linear. M1 is off and M2 is linear, so capacitor gets a discharging path. So this is about the working of CMOS inverter. Now let us discuss different effects related to MOSFET. First is channel length modulation. Whenever the device is operated in saturation mode, then MOSFET transistor acts as a perfect current source. That means in that case, IDS is drain to source current remains constant even if VDS, that is drain to source voltage, changes. But practically it's not true. Whenever VDS changes or increases, the depletion region at the drain junction increases. This upward arrow indicates values are increasing and the effective length of a channel gets reduced. This concept is called channel length modulation. Actually, there is one term which is called pinch-off condition. So as VDS goes on increasing, VDS is drain to source voltage. As VDS goes on increasing, this pinch-off point moves towards source terminal, that is away from the drain terminal. So effective length of a channel gets reduced. It is the channel length modulation. Next is the concept of velocity saturation. In case of the charged particle, the V, that is velocity of a charged particle, is linearly proportional to E. E is applied electric field and the proportionality constant is denoted by mu, where mu stands for mobility of a charged carrier. As shown in this diagram, this is the graph of VD, that is velocity of a charged carrier, versus E, electric field, applied electric field. Initially the graph increases, fairly increases VD with respect to E. But once the value of E, electric field, reaches a critical value, that is EC, the graph will not increase. That means velocity will not increase. It remains constant. This is called the saturation velocity. So when E reaches EC, velocity of a charged carrier tends to saturate. That means this value will not increase further. it will be limited only up to this extent, V saturation. So velocity of a charge carrier tends to saturate and value of mobility mu decreases. This typical value of saturation velocity in case of a MOSFET transistor is 10 raised to 7 centimeters per second. Next important concept is body effect. Uh, Usually, if there are similar types of MOSFET, that means if all MOSFETs are of N type or P type, then they are fabricated on a common substrate. The substrate voltage of each device remains same, and to keep the substrate to channel junction in cutoff condition, the substrate is connected to the most negative terminal. But in practical cases, number of MOSFETs are connected in series one after the other. As shown in this diagram, for the lower MOSFET, VSB is source to bulk. Bulk means substrate. So source to substrate voltage is 0 for the lower transistor. As you move in upward direction, for the upper MOSFET, VSB is not equals to 0. That means there is a difference between source to bulk voltage. The net effect of this is, as we move in the upward direction in this particular designing, then VSB will go on changing, will go on increasing. So this net effect is there will be increase in the value of VTH. VTH is the threshold voltage. This change of VTH with respect to VSB, because VSB is not remaining 0, it is increasing. So due to increase in VSB, VTH, that is threshold voltage, increases. This effect is called body effect. Next important part is hot electron effect. Under the thermal equilibrium conditions, electrons and holes constantly absorbs as well as emits the photons. That means they are absorbing and emitting the energy lines. So average gain in their kinetic energy is 0. But when electric field is applied, then in the presence of electric field, kinetic energy of charge carriers starts increasing. Upward arrow indicates values are increasing. Therefore, the velocity of such charge carrier increases as E increases. Typically, whenever electric field E becomes 100 kilovolt per centimeter, then velocity increases. The carriers does not remain in their thermal equilibrium conditions, so it will cause the effect which is called impact ionization. It produces avalanche multiplication, means, make it more simple, more number of electron and hole pairs are generated. So these charge carriers inject in the oxide layer and it may damage the IC. To get the protection from this, the effective solution is reduce the electric field at the drain junction. To reduce electric field, you can change the doping concentration at the drain junction, or you may use additional MOSFET in series with the existing MOSFET which is getting affected, so that the available voltage will be distributed among the two MOSFETs. So this is about hot electron effect. Next part is combinational logic design. So we are making use of a Cmos. This is the generalized diagram. It makes use of PUN, that is pull up network, connected in series with PDN, that is pull down network. Input is applied to both PUN as well as PDN. This pull up network, as the name indicates, is used to produce logic 1 at the output, because this is VDD. So PUN connects VDD at the output. PDN is connected to ground, so it is used to make this output low, because it will be connected to ground through PDN. In case of PDN, while designing PDN, always NMOS is preferred, because NMOSFET produces strong zeros, strong logic 0. For PUN, that is pull up network, PMOS is preferred because it produces strong ones. Now, how to implement AND gate? Equation is A dot B. This is the diagram. We are using N MOSFET. They are connected one after other. That is, they are connected in series. A and B are two inputs. So this circuit conducts when both A and B are high. Next is OR gate. Equation is A plus B. This OR gate is obtained by connecting N MOSFETs in parallel. Again, A and B are two inputs. So it conducts if A or B is high. Next is NOR gate, that is not OR. Equation is A plus B. This equation bar or A bar dot B bar. This is the circuit diagram in which P MOSFETs are connected in series. This is the symbol of P MOSFET. So it conducts when both are low. Next is NAND gate, that is not AND. So it is A dot B bar. This is the equation of AND gate. So A dot B bar, which is same as A bar plus B bar. It is obtained by connecting two MOSFETs in parallel. So it operates if any one input is low. Make the thing simple. How to remember it? This is the diagram for AND gate in which we are using two N MOSFETs in series. NAND तैयार करना है तो ये series का parallel करेंगे, N MOSFET के बदले में P MOSFET यूज करेंगे. Same technique. This is the diagram for OR gate. Here we are using N MOSFETs in parallel. NOR चाहिए तो ये parallel का series कर लो, N MOSFET के बदले में P MOSFET यूज कर लो. So this is the diagram for NOR gate. Now let us solve one numerical. The question is design CMOS logic for given Boolean expression is y is equals to a bar b plus ab bar. Now remember simple rules. This table shows different rules. Actually the rules are pretty simple. If dot is there, that is multiplication sign. If you are using PMOS, make use of parallel connection. For NMOS, make use of series connection. If plus sign is there, for PMOS, make use of series connection. For NMOS, make use of parallel connection. We know that the CMOS logic consists of PUN, that is upper portion, upper part of the network, and PDN, that is lower part of the network. So for designing of PDN, NMOS is preferred. For designing of PUN, PMOS is preferred. Now this is the given expression. First step, we'll first draw the PDN. Whatever the diagram I have drawn with blue ink is for PDN. So first term is A bar B. Actually it is A bar into B. So this is into sign, multiplication sign. For NMOS, we know that for the lower part PDN, we have to make use of NMOS. For NMOS, dot indicates series connection. So I have drawn two NMOS in series. Inputs are A bar and B. So this is A bar, this is B. Plus sign is there. Plus sign for NMOS indicates parallel connection. So in parallel with this, I have drawn one more branch. Again, two terms are there, A, B bar. So it is actually A into B bar, A dot B bar. So again, dot sign indicates series connection. So I have drawn two NMOS in series. The inputs are A and B bar. So A and B bar. This is the PDN network. Now for PUN, you don't have to again apply the rules. Make it more simple. कैसे याद रखना है? PDN पर एक बार डिजाइन करने के बाद यहाँ पे जो सीरीज हो वो PUN में पैरेलल में ड्रॉ करना है. फॉर एग्जांपल दिस ब्रांच इज अ सीरीज कनेक्शन, वो पैरेलल में ड्रॉ कर लो. दिस ब्रांच इज अगेन इन सीरीज, वो पैरेलल में ड्रॉ कर लो. और फिर ये दोनों जो यहाँ पे पैरेलल में था वो सीरीज में कनेक्ट किया है. Or if you are finding it difficult, make use of this table. But keep in mind, whenever you are making these changes, जैसे मैंने बताया ये सीरीज का पैरेलल में ड्रॉ करेंगे, ये सीरीज का पैरेलल में ड्रॉ करेंगे, and then we will connect the two things in a series connection. But keep in mind, for PUN, always PMOS is used. So this is the symbol of PMOS. So notations are A bar, B, A, B bar. So this is about the PUN network. What we learned, for PDN always use NMOS, for PUN always use PMOS. But keep in mind the CMOS logic always produces inverted output. So this is the given equation. Actually we are getting the output like this, A bar B plus AB bar, and then again inverse of this. So to obtain the original output, at the output side we have to draw one inverter circuit. Inverter circuit consists of this circuit, which is PMOS and NMOS connected one after other. So this produces inverted output. So after taking inversion, this bar sign will get vanished and you will get original output like this. So this is the way how we can draw the combinational logic design using CMOS. Next part is transmission gate logic. Transmission gate makes use of two MOSFETs, NMOS and PMOS, which are connected in parallel with each other. We know the basic characteristics of NMOS. NMOS passes strong zeros and weak ones, whereas PMOS, on the contrary, passes strong ones and weak zeros. So we have to take advantage of both the things. So two MOSFETs, NMOS and PMOS, are connected in parallel. This is shown in this diagram. So this is NMOS, this is PMOS, which are connected in parallel. C and C bar are control signals. A and B are the signals which are taken out from either side. So if C is equals to 1, see, if this C is equals to 1, NMOS is on. Now C is 1 means C bar is complement of C. So C bar is 0. So PMOS is also on. Remember it like this. NMOS is on when this is high and PMOS is on when C bar is low. So when C is 1, C bar is 0. So both MOSFETs are on, and whatever signal A is there, that will be available as signal B. If C is 0, then NMOS is off, then C bar becomes 1. If it is 1, there is a bar over here, there is inversion action. So PMOS is also off. So both the transistors, both the MOSFETs are off. So it acts as an open circuit. Now this is the symbol of transmission gate. Two arrowheads are drawn like this. That means if you want to draw the symbol, one triangle is like this. Draw another triangle and another arrowhead like this. So this is the symbol of transmission gate. Upper part is for PMOS, so bubble is there. Lower part is for NMOS. In this diagram, in this symbol, X and X bar are control signals. Now, how the operation takes place? Like we have discussed in this case, whenever X is 1, NMOS is on, PMOS is also on, because X is 1 means X bar will be 0, so PMOS is also on. ये diagram इस diagram से I mean थोड़ा अलग है, different है. So here I have shown control signals X and X bar vertically. In this case, C and C bar control signals were shown horizontally. अब देखो, when X is 1, NMOS is on, PMOS is also on. So whatever amount of A is there, that will be available at B. So this gate will pass the signal A, input signal A, and it will be available as output signal B. So if A is 0, output will be 0. If A is 1, output will be 1. मतलब जो input हम लोग यहाँ पे as A input apply करेंगे, same input, same signal will be available as output B if gate is activated, if this transmission gate is active. Now, this is the case when X is equals to 1. If X is 0, so if this is 0, X bar becomes 1. So since this is 0 and X bar is 1, both the gates, NMOS is also off, PMOS is also off, so the gate will be open, and in that case the circuit works as high impedance state, high impedance circuit. So this is the way how the transmission gate logic works. Next part is Latch-off effect. Actually, if we are talking about a CMOS structure, then it is containing many number of NMOS and PMOS transistors. So as shown in this diagram, this NMOS and PMOS are interconnected. The different terminals are shown. Source, gate, drain terminal for NMOS. Same way, drain, gate and source terminal for PMOS. The output of NMOS is connected to the base terminal of PMOS transistor. So if NMOS starts conducting, and if it happens that the current which is applied to PMOS goes on increasing, then it may damage this PMOS transistor structure. So to limit such things, there is a crucial role as far as this N-level structure and P-type of structure is concerned. This produces certain opposition. Now, actual latch-off effect takes place between the source terminal of NMOS transistor, then P-type of substrate, N-level, and again to the source terminal of this P-type of MOSFET. So this is about the latch-off effect. Many times, to avoid the excess flow of current, some guard rings are preferred, they are used in such structures. So dear students, that's it for quick revision session of this unit. So thank you. Thanks a lot for watching this video.